current slide. All right. All right. All right. Good deal. Number is back. I know you're in there, but there. And Caitlin's here. And Cynthia's here. All right. All right, so right now we're just missing, wait, I'm sorry, Jeremiah's here. All right, I'm sorry. Just put you down now. Okay. I'm missing Cynthia, Christian, maybe the first day in 2 terms that he's missed, Cody, Stephanie, and Devin. Right. Yeah. Okay. Good deal. Good to see all of you here. Okay, let me go over a few of these announcements. We missed class completely last Thursday, but of course, part of that was several of you were getting awards, okay, and congratulations to all of you who did get awards at the Honors and Awards Day. They came out, published a final exam schedule that I'm not sure is correct. Most of it is. They just have the starting finals on Monday the 29th, whereas the college calendar, academic calendar, says that's the last day of class. So I don't know what the rationalization of that has been, but anyway, the rest of it should be correct. Except for one place on page 2, they say grades should be in the system. They're talking to us no later than noon on Monday, May the 8th. May the 8th is not a Monday, that's a Wednesday, but on the next page they say Wednesday, May 8th. So another error there, but that one they corrected themselves. Now, the administrative calendar, which is sort of an important thing. Let's sketch where we are now. 1 week from today, today's the 16th, 1 week from today is the last day to withdraw from a class for either full-term or mini-term, second mini-term courses, I believe. I believe that's correct, okay? And that's one thing I wanted to make sure that you knew, and so spread that around. Not that any of you need to withdraw, it's the people not here that might need to withdraw. So if you know some of those folks, let them know. Like I say, if anyone wants to see who was involved in Honors and Awards, I have that program here. And I think the rest of it is pretty much, I've made all those announcements before. So, good deal. Any questions? Either administrative, yes.
Will we have any more testing here besides our
A
finals?
little bit louder.
Will we have any more testing here besides our final?
Yes, we'll have a test on chapter 6. Now, it may be given at the same time as your final as a take-home the last day of class. Just depends on how far we get. Doesn't look like we're going to finish the chapter in time. So the last test for chapter 6 will be a very short test, not nearly as long as the first 3 have been. And then the final will also be very short. So the 2 of them together will be as short or shorter than any of the others.
Our final is take-home?
Is take-home also. So you'll get your last chapter test and more than likely the last chapter test and the final on the last day of class, which is the last Thursday of this month, which is just a week from this coming Thursday, I believe it is, isn't it? I believe that's, oh, here's a calendar right here. Let me see it. We're now on the 16th. We'll have class on the 18th, the 23rd, and the 25th. On the 25th, I will, number 1, return all your other tests to you, so that's the last day possible to get your other tests turned in. Okay, please get those in, preferably before that Thursday, so I can get them back to you. Okay, that's also the last day to get your research paper in. And right now, fewer than half of you, 1, 2, 3, 4, 5, 6 have turned in a research paper. So more than half of you haven't done your research paper, and quite a few of you have not turned in. Let's see, there's 2 people haven't turned in test 1, 1 present and 1 not present. Test 2, several people haven't turned in test 2, and test 3, no one has turned in yet. So please get those in soon, okay? Because we only have 4 today and 3 more classes. That's it. Yes?
Okay. So our last 2 tests we're getting that next Thursday, right?
Yeah, a little louder.
Chapter 6 and our final we're getting that next Thursday, right?
Yeah, you'll get that. Yeah, Thursday week. What's that?
When do you want us to turn it in?
Okay. And that, I was just going to get to that. I'm glad you asked, though. Are any of you graduating this term? 1, 2, 3. Okay. For you people, I have to have it in by the following Thursday because your grades have to go in by Friday. Okay. So you'll have 1 week to do those 2 tests. Okay. And they're, like I said, they're going to be short, pretty much to the point. You got a weekend to work on them, get them done. Okay. The rest of you who are not graduating this term, anytime that week. Okay. Anytime during finals week, which goes through Monday of the following week, because classes technically, according to the administrative calendar, everything else, classes go to the Monday. They just don't go. Monday the 29th is the last day of class, so the last day of finals is May the 6th. So you can have yours turned in anytime up. Those not graduating, turn yours anytime up to May 6th. But I've got to have them in by May 6th because your grades are due by noon on Wednesday the 8th. Okay, but yours are due, I think, noon on Friday. So please get them to me by Thursday so I have plenty of time to grade. Okay? Good question. Does that answer what you needed? Okay. All right, good deal. Any other questions? Administrative or trigonometric? Okay. All right. We started 6.2 the last time we met, which was last Tuesday. I'm sorry we lost the last class. We would have gotten much further along. But here is the first of our law of cosine type problems. Find the 3 angles of this triangle. Notice they give you the 3 sides, so this is a side, side, side problem. We need to know the 3 angles. Okay? Since we know the 3 sides, it might seem to you it doesn't matter where you begin. It does. Okay? Whenever you have the 3 sides of a triangle, what can you tell me about the 3 angles here? There's the 3 sides are 8 feet, 14 feet, and 19 feet. What can you tell me about the 3 angles? You can't give me the value. If you can, you're really good. But you can give me a relative. Give me some relations. B is the largest angle. That is a great thing to notice because that's where you begin. Because you see, with the law of cosines, with law of sines, it doesn't matter if it's acute or an obtuse angle. First and second quadrant sines are always positive. Didn't really matter there. But with cosines, they're positive in the first quadrant, negative in the second quadrant. So if that happens to be, and it sure looks like it's going to be an obtuse angle, you better deal with that one first to find out whether it's acute or obtuse. And I think you'll see it's going to turn out being obtuse. So let's start with that. We're going for angle B. Now, does anyone remember how the law of cosine works? The law of cosines, okay, whatever that is. Remember how it's stated? Somebody come up with it.
A squared equals B squared plus C squared.
Okay, say that a little louder.
A squared equals B squared plus C squared minus 2BC cosine A.
Okay, but that's cosine A. We don't want that one yet. Okay, which one do we want? We decided we were going for B first. So how does that one go? B squared is equal to A squared plus C squared minus 2 AC cosine capital B. We want that one first. So that's the law of cosines, and to me, the easier form to remember. Okay? So let's solve this for cosine B. So what would you do first? I would move this to that side because that's a minus, right? So let's add 2AC cosine B to both sides. Okay? And at the same time, let's subtract the B squared from this side. Okay. So that'll get rid of the B squareds here and give us a 2AC cosine B over here is equal to A squared plus C squared, those go away, minus B squared. And now, do what? Divide by 2AC. 2AC. All right, and that gives us cosine B. Cosine B is equal to that. See, all on this side we know, A, B, and C is the B that we don't know, capital B, the angle B that we don't know. So let's isolate that over here and go to town with this. So now, plug and chug, folks. What do you get? A squared is 64 plus C squared. I can't do that in my head. I think it's 196 maybe. Whatever it is. I believe it's one. I'll just put 14 squared. Let you figure out what it is. Minus B squared, which is 19 squared, divided by 2 times A times C. Well, A times C is, ooh boy, I'll just write it down. 16 times 14. Okay. Someone do the math. What do you get? Bet you get a negative number, don't you? That's why we need to start with the biggest angle. When you got side, 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 always go for the big angle first. Okay, and what does that give you?
It's negative 0.45.
Okay, so that's cosine B. So how in the world do we get B?
The inverse cosine.
Second?
The inverse
Inverse cosine. Do you want it in degrees or radians?
degrees.
My guess degrees, so be sure you're in degree mode. So B would then be, better be an obtuse angle, is it?
We get 116.74.
116? Is that what you said? 116 point what? 74. Let's make it 117. Okay, I know the book doesn't do that. 117 degrees. Because you see, we only have one significant digit here, 2 there, 2 there. I can't see giving 5 significant digits there. You just don't have justification. You really don't have it for 3, but I'll accept 3. Just the nearest degree, 117 degrees. All right, next. You got one angle, 117 degrees. But don't erase that from your calculator, okay? Keep that, all those digits in there, okay? As many as your calculator stores there, keep them, okay? Because what are you going to do next? You got 2 options. What you want to do?
Use the law of sines and solve.
Absolutely. Now, if you're going to use the law of sines, because that's easier, you have a ratio you know, and that's why I say keep that in there, because whatever that in there, do the sine of it. Maybe not quite yet, but you're going to do that. So that's why I say keep that whole angle, all those digits in there, okay? And then how will the law of sine set up? Literally, you don't have to put in the numbers, or you can. What would that be?
8 over sine A.
Okay, you're going for that one. So we're doing 8 over sine A is equal to
19.
19 over the sine of whatever that big old number you had, 116 point blah, 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 okay? I'm going to put 117 because that's where I stopped writing. But what you're looking for is sine A, and that's equal to the product you know, 8 times the sine of 117 or 116 point blah, 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 divided by 19. Okay? So that's why I say keep that number in there, do the sine of that, multiply by 8, and divide by 19. And that gives you sine A, and then do the inverse sine, and what do you get? Should be a pretty small angle.
It's 0.3758.
Okay, that sine of A is 0.375 something or another, you said? Okay, whatever that is. And then what is A?
22.07.
Okay, wait, let me. About 22 point what?
07.
Okay, let's round that to 22 degrees. Okay. Now, that would be A. That looks reasonable because it's a pretty small angle. Okay. Now, my next question to you, you want to find C using law of cosines or law of sines? Say again?
Can't you just add that?
Absolutely. The answer is no. Okay. You want to use the sum of three angles is 180 degrees. So just add those two together. That gives you 139. Subtract that from 180, and that gives you 41, I think. So let's guess 41 degrees. Now, let's see if this even makes sense. Well, the biggest angle is opposite the longest side. Yes. The smallest angle is opposite the smallest side, shortest side, and the medium angle is opposite the middle side. Yes, they seem very reasonable, don't they? Any questions? Okay. Let me erase my scratch here and see. I'm sure the book carried it to 3 or 4 decimal places, so no, 2 probably. Let's see what they did. It's a good idea first to find the angle opposite the longest side, okay? And then they use what they call the alternate form, which we got because you gave me the other form, and then we calculated it exactly like this, and you plugged it in, and that gave you a negative 0.45, blah, blah, blah. And when you took the inverse sine of that, you got 116.80, blah, 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 or 79, so whatever. And at that point, you use the law of sines, and I kept the whole thing in there and did the same math. You got that, and that B is obtuse. The triangle can have at most one obtuse angle. You know that A must be acute, of course. And so that was about 22 degrees, and the difference of those is 117. No. C would then be the difference of those, which would be about 41. I think that's what we got, right? Yeah. Okay. So carry around those extra decimal places. You just don't have justification, and you get close enough answers. Okay. Any questions on that? Did you go back and see any of it? Yay or nay? All right. All right. There is a checkpoint. I highly recommend you do the checkpoints as soon as possible after class, just to refresh your memory on what's going on. I don't see this exact wording in the book. Yeah, there I see it. This is on the top of page 410. Do you see why it was wise to choose the largest angle first? Because and this is just like I said, the cosines are positive for acute angles and negative for obtuse angles. And if you do that biggest one first, you're going to find out whether it's acute or obtuse. Also, if you do the biggest one first, they made a point of the next one's got to be acute. Well, guess what? In any triangle, if you do the biggest angle first, whether it's acute or obtuse, the other two have got to be acute because they can't add, they add to a 180, and you can't have one more than 90, and the other two add to anything greater than 92. So it's got to be less than that. So in example 1, once you found that angle B was obtuse, you knew that the other two angles had to be acute. But if you go for the largest one first, guess what? The other two are going to be acute whether the first one's acute or not. If you go for the largest angle, the next two have to be acute. So they make it seem like A and C could have been anything other than acute. If B was the biggest angle, A and C are guaranteed to be acute, because you can only have one obtuse angle in a triangle, if you have it. Furthermore, if the largest angle is acute, then the remaining two angles are also acute. So they say the same thing. Okay. Now, they're skipping example 2, so let's go back and do example 2. All right. This is the Sassy case, given two sides and the included angle. And you can go to larsonprecalculus.com for an interactive version of this type of example. So here's what they give us, and I'm going to have to draw it, so it's not going to be pretty. Okay. I'll first draw the line AB. It's supposed to be horizontal. It doesn't quite look like it is. And then I'll come up here to C, and then come down here to B. Okay? And this, of course, then will be side A. This will be side little b. This will be side little c. Okay? They give us B. Little b is 9 meters, which is pretty far. Angle A is 25 degrees. Mine may not be drawn to scale. And side C is 12 meters. Again, a pretty good sized plot of land here. Now, how would you go about solving that triangle? You need to know 2 more angles and 1 side. What you go for first? A. You got to, little a, because you have really no choice. So what's the equation that gives you little a? It doesn't really give you little a. It gives you little a squared is equal to, second, b squared plus c squared. What's next? If that was it, that meant this was a right angle, right triangle. It's not. Okay, so you have to have more. Minus 2bc times the, what they call it, law of cosines. Cosine of A, the angle we know. So you see, everything we know is on the right-hand side, and one of the things we don't know is on the left. So that's what we go for. So let's sock it to it. B squared is 81. And by the way, it's square meters. Plus C squared is 144. Again, square meters. Minus 2 times 9 times 24. Well, I'm just going to do 18 times 12. I'm not up to doing that in my head right now, times the cosine of 25 degrees. Okay. Someone with a calculator, let me know what that gives us. It better be a positive number because this thing is squared. Okay. If you come up with a negative number here, we have problems, Houston. Second?
I got 29.237.
Okay, that would be a squared, right? 29.227. Don't, huh? 237. Okay, don't erase anything there. Just while it's on the screen, take a square root of it. Something between 5 and 6, right? Closer to 5, right? What you get? A little louder? Someone do it? Okay. Okay, let's call it 5 because they don't give you, let's call it 5 meters. Okay, I would hang on to the other digits there. Don't throw them away. Don't clear your screen. But for answer purposes, that's about 5 meters. Okay, now what would you do next? Don't erase your screen, but what would you do next? Anybody? Now that you know little a and capital A, hint, hint, what would you do next? Law of signs, okay? But keep all those digits on there for A. I just wrote down one digit because that's all you have here, but keep them all there. And how does the law of sign go? You remind me. Second?
I'll do it differently.
Okay.
So sine of 25
Okay, so he puts the sign on top. Sine of 25 degrees over 5 point blah, 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 blah. I would hang on to that. Okay, is equal to. Now, the question is, which do you do next? Okay? Now, looking at this, that looks like that is, well, that's actually your longest, biggest angle. It's got to be. Whether my drawing is accurate or not, it's the largest angle, for sure, right? So, it could be obtuse or it could be acute. And because sine can go either way and still be positive, I would go for the smallest angle here, because that's got to be acute. There will be no ambiguity here if you go for the smallest angle. The law of cosines, go for the largest angle first, but law of sines, in this situation, go for the acute, because there's no ambiguity. If you didn't see, you'd say, which is it? Is that the acute or the obtuse? Because I bet you'd have one that could go either way. Even if it is acute, it could have been obtuse. So go for the acute angle. You remove ambiguity there. So that would be the sine of B, right, divided by what? 9. Okay, so your sine of B is equal to 9 times sine of 25 degrees divided by that number that you kept there, 5 point blah, 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 blah. Okay. Now, that's hard to do here, since that's all that's on your screen. So I would do 1 over this. You know, that's on your screen, 1 over that, then multiply that by 9 times the sine of 25. See what you get. Okay. You can do it any way you want to, but me being lazy, okay, this is the way I would do it. Since you have this on the screen with all those digits I didn't write down, I don't want to type them all again. So since you have that on the screen, do 1 over x for that. That moves it up here. Then multiply that answer by 9 and that by sine of 25 degrees. That should give you the sine of B. I'm just being lazy. I don't like to do any more typing on that computer than this. Huh?
I don't have that type of calculator, so I'm trying to figure out.
Oh, your phone will do that, won't it? You don't have a 1 over x key on? X to the minus 1 key? Oh, you have a calculator. No, phone. Okay.
I don't didn't do that. But if you do square root of 29,
Okay, wait. Okay, I don't even know where you are. Yeah, well, I would have kept the bigger number there, but it's okay. This will still work. Okay. No, what'd you get? That's still going to be good. 5 point something, right? That's going to be close enough. Okay? Okay, you do a square root of it? That would be that one. Okay? That's 5.4, blah, blah, blah. Okay? Now, what I would do with that is then do a 1 over x key. Right there. See it? Okay, do that. That does reciprocal. And times 9 and times 25 sine equal, and then you take the inverse sine of that. I think that's going to be your second key here. Yeah. Inverse sine of that. Got 45 degrees. Is that what y'all got? 45 degrees. So that's approximately 45 degrees. That was B. Okay. Now, law of sines or law of cosines? Neither. Add those two together and subtract from 180. Add those two together, you get 70. Subtract that from 180, 110. Okay. My guess. You tell me how good we did. The book gave us, B was, well, whoa. I must have really botched something up here. Did I? No. Oh, they did it unlike what I suggest. Oh, no. Okay. No, they did it right. They said B was either going to be 45 or 135. Well, guess what? It can't be 135 because it's the middle side. You know, this is 25, this is 9, and that's 12. That's going to be a short side. This is an acute angle. That's got to be acute. Okay? This has to be the big angle. So this one's got to be acute. Why even suggest that it could be 135? It can't be. It's got to be acute. So it's set to be 45. They said 44.70, which is, I think, pretty close to what you got. So don't be messing around with 135. It's not. Okay, so they take you through all sorts of extra work that's not necessary. Okay, you know that's the acute angle because this is that's got to be a short side, and it turns out being a short side. This then is the longest side, so you know this is the biggest angle. This one's got to be acute. So don't even suggest that you use 135. It can't be 135. So you don't have an ambiguous case here. You have 45. And with 45, that gives the other angle to be 110. And why in the world suggest that C2 could be 19 or 20 degrees? It can't be, not with C being the longest side. So to me, they take you through all sorts of extra stuff, not necessary. Once you have that A there, you know this has to be acute because that side is shorter than that side. This one could be acute or obtuse. It doesn't matter. That one's got to be acute. So don't even introduce a 135. It can't happen. Go with 45. That gives you 110. You're solved. Okay? Make sense? It's nice for them to carry all that out, but it's totally unnecessary. Okay? There is a checkpoint. Do the checkpoint. All right. Any questions? All right. They carry, of course, too many digits. But hang on to the digits as long as you're doing calculations, but for your answer, round off to the significant digits. All right. Now I think we're ready for our applications. Any questions before I leave it? I thought I heard something. All right, here's example 3, an application. Okay. The pitcher's mound on a women's softball field is 43 feet from home plate. There they're drawing. And the distance between the bases is 60 feet between each base. Now, the thing they don't say here, but they show it in the picture, every base is a right angle. They don't show this one, but if this one and this one are right angles, then that one and this one have to be right angles as well. Okay? So, they do tell you this. The pitcher's mound is not halfway between home plate and second. Okay? It is not. So don't make that assumption. Now the question is, how far is the pitcher's mound from first base? Okay? From first base, not home plate, but first base. Well, what they told you, pitcher's mound is 43 feet from home plate. That's the first thing they said. And that the bases are 60 feet apart. So you know this one. Okay. Now, that's all they told you. But I will tell you this, they didn't tell you this. Even though the pitcher's mound is not halfway between home and second, the pitcher is equal distance between first and third. They don't have it over here or over there. It's smack down the center line. And if that's the center line and each of these are 90 degrees, then that means this has to be 45 degrees. So that's how they got to write that on there. Okay. Now what they're looking for is that distance there. If you haven't figured out why they named them this, home plate was capital H, so therefore that's the representation of the 45 degrees. This length would then be little h because it's opposite the 45 degrees. The pitcher's mound is angle P here, so they put little p as 60 feet. If you thought that should be F or something else, no. And then this little f is opposite first base, capital F being first base, which is not 45 degrees. You can't make that assumption either. That's not 90 degrees, so this side is 45 feet. What does this set up as? Yeah, this is side angle side. SAS. SAS. Okay. Now, what we're looking for is how far is the pitcher's mound from first base. So H is going to give you that answer. What can we use? Exactly. Okay. Law of cosines, which was H squared is equal to F squared plus P squared. What else? Minus 2. What else? F, P, cosine, H, capital H. Okay? We know everything on the right, and we're looking for the left. Okay? So this will be 43 squared. I'm not about to try to do that one in my head. Plus 3,600, I can do that one. Minus 2 times F, which is 86 times 60 times cosine of 45. I know what cosine of 45 is, don't you? Please say yes. 43 squared plus 3,600 minus, I could even done that one, couldn't I? 0, 6, 48, and 3 is 51 times root 2 over 2. Okay? I still will need a calculator, but that would be 2580. What you get H squared to be? Remember, that's H squared, it's not H. Should be a pretty hefty number. Bless you. Greater than 1,600, right? What you get it to be? Anybody? Little black boxes take a long time, don't they? Okay.
Yeah.
Anyone got an answer yet? What?
I got the final answer. I don't have that answer.
I'm sorry?
I have the final answer, but not that answer.
Oh, that's all right. What's your final answer? That's all I'm interested in. 42.43, which we can't really justify that many digits. That's what the book got to. I would say that was about 42 feet. You could say 42 and a half if you wanted to. That might be a little bit more, a little closer, but, that pitcher trying to pick off the runner at first is going to say, I got to remember about 0.3 feet there, 0.43 feet. Nah, A little over 42. Okay. All right. Want to see how they did it? Anyone not get that answer? Have questions before we move on? So let's see what they do next. In the triangle HPF, where H is home plate, P is pitcher's mound, and F is first base, I'll capitalize that H is 45 degrees. That angle H is 45 degrees. The line HP bisects the right angle at home plate. Yeah, home to pitcher's mound is exactly bisects that, so that's 45 degrees. F is 43, that was given, and P was 60, that was given. So we use the law of cosines, which is H squared is equal to F squared plus P squared minus 2FP times the cosine of H. And that gave 43 squared plus 60 squared minus 2 times 43 times 60 times cosine 45, which came out about 1800.3. I'd say 1800 is pretty close. And take the square root of that, and that would be about 42 feet. Okay, about 42 feet. All right. Now, let me go back to our picture here a moment, just to let you see it kind of is making sense. If this is 45 degrees, okay, that means that this distance, now this by itself doesn't mean this. This is just a little bit beyond halfway, okay, by the picture here. We don't know that for certain, but that makes sense for it to be. So this has got to be longer. This side has got to be relatively close to the same length of that. Not the same, because this is a 90-degree angle, but this is close enough to 90 that this has to be pretty close to 45. So you expect it to be I would have expected, just by the picture, this to be, oh no, I guess that's right. It's just a little shorter, but not a lot shorter. Pretty close. And sure enough, 42.43 is pretty close to 43. So 42 feet is a very reasonable answer. Okay? Now, there is another illustration they don't give us. So this is example 4. So let's do example 4 here. They like these water races, don't they? Okay. A ship travels 60 miles due north and adjusts its course. So 60 miles due north. Now, they don't say nautical miles, they're just saying miles. Then adjust its course is shown in figure 6.9. Okay? So it just adjusts its course. And that's all they tell you. Okay? After traveling 80 miles in the new direction, okay, they didn't say how they adjusted the course, just 80 miles in the new direction. It's now 139 miles from where it started, from the point of departure. Okay? Describe the bearing from point B to C. So they named this one A, this one B, and this one C. So they want you to describe this angle right there, from B to C. Okay? Now, what you have here is a side problem, which obviously what law do you use? Law of cosines. Okay, of course. That's the section we're in. Okay. Now, which angle is related to the angle we're really interested in? Angle B. And guess what? That's the best one to start with anyway. Why? It's the largest angle. So that's the one you need to start with. Once you have it, then you see the supplement of this angle is going to be the angle you're looking for. Right? To give you the bearing of C from B. That's my understanding of what they're asking for. Describe the bearing from point B to point C. Okay. So, how would you do this? What would be your approach? You can start with whichever form you want it in. How would you like to start?
Cosine B.
Okay, he's going to start with what they call the alternate format, which I don't care which is. Cosine B is equal to A squared plus B squared, no, plus C squared minus B squared over, okay, my writing really stinks here. Let me see if I can clean that up a little bit. Okay, that's better. I can get my pen back. Over what? 2AC. That's it. We know everything on the right. We're looking for the angle at the left. So what would this be? This would be A, which is 80 squared. That's 6,400. Plus C squared. That's 3,600. I think I can add those two. Minus B squared. I sure can't do that. That's 139 squared. So I'll let you do that on the calculator. And we'll divide that by 2. Let's see, that would be 4,800. That would be 9,600, I think. I'm doing this in my head, so it's subject to great error. 9,600. Now, just anticipating here, it's going to be a negative number. No doubt, right? What do you get?
It's negative 0.97.
Blah, 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 blah. Okay, now, go on and do the inverse cosine of that.
That makes it 166.
166.
0.14.
Okay, we'll round to there. Now, how do we get the bearing?
Oh, we subtracted by what?
Subtracted from 180. Yeah, subtract that from 180, and you get the bearing would be north 14 degrees west. That would be the bearing in my mind. They did 13.86, which that's close enough to 14 degrees west. See how that works? Any questions on that? Obviously, an obtuse angle there. So even if it had asked for what's the bearing of C from A, you still start with B. Otherwise, you could be dead in the water. Aha. Okay, never mind. Unintentional pun, but still okay. There is a checkpoint there which has another figure at the left. Any questions? All right. All right. Let's move on to, oh, wait, they have, no, they don't have this one. So, Heron's area formula. Now, we have 3 ways to calculate the area of a triangle. The good old standard that you learned back in grade school was 1/2 the base times the height. Okay, base was usually easy to get. The height was a really difficult thing to determine in a real life situation. Because if you have some strange looking angle there, a triangle there, you can always get one side and call that the base, but how do you determine what the height is? That needs to be the perpendicular distance here. If you're out here with a ruler, how are you going to determine a perpendicular distance? But it's a very simple formula, 1/2 the base times the height. Okay, in the last section, law of sines, we found that it's 1/2 if you knew 2 sides and the angle in between, it's 1/2 the product of those times the sine of the angle. But how do you know the angle in between? That's not something that's usually well known. Yeah, you can measure that side and this side, but you'd have to have a sextant and estimate what's the angle in between, and that's not really easy to do. Heron's formula is the third way, and that's a piece of cake because you can always measure the three sides of a triangle. Okay, the law of cosines can be used to establish the following formula for the area of a triangle. This formula is called Heron's area formula after the Greek mathematician Heron. And he was about 100 BC, way back there, okay? So guess what, team? This guy knew what he was doing way, way, way back. And by the way, this could be a paper topic. Who in the world was Heron? What was he like? Or how did he determine this area formula? Or what are applications of it? There could be several paper topics there. But here's what we've got. Given a triangle with the sides of length A, B, and C. And those are easy to measure. Measure its length A, length B, length C. Okay? Measure the three sides. How do you find the area? Well, it's this. It's the square root of S times S minus A times S minus B times S minus C. What in the world is S? We weren't given S, were we? S is what we call the semi-perimeter. Now, how did he come up with this? I'm not sure. That'd be a good paper topic. You add the three together and divide by 2. Semi means half of the perimeter. The perimeter of a triangle is add the three sides together, how far it took to walk around. Take half of that, that's your semi-perimeter, and then multiply it by the difference of it in A, the difference of it in B, the difference of it in C. Multiply those four together and take the square root. So what units are you going to use to measure that? The lengths of the sides. You tell me. What unit? Meters, okay? So we've got so many meters by so many meters by so many meters. Well, S is going to be meter plus meter plus meter divided by 2. That's going to be so many meters. So this is going to be a meter times difference of 2 meters, difference of 2 meters, difference of 2 meters. That's going to be meters to the fourth power. Square root of it, you take the square, you half the exponent, and you get square meters, exactly what you need to measure area. So the units worked out quite nicely too. Okay? So let's go to town with it. Find the area of a triangle having sides of lengths 4 meters, 43 meters, 53 meters, and 72 meters. What's the first thing you better find out? What S is, and what would S be? Second? 84 meters. Boy, he did that in a hurry, didn't he? The book has it right. Okay. So, add those three together. That gives you 96 plus 72. Had better be 168, and half of that is 84. Very good. What do you do with that? What's your area then? The square root of 84 meters times the difference of that and A, that would be 41 meters, times the difference of those two would be 31 meters, times the difference of those two would be 12 meters, right? They made it easy, didn't they? Okay. Someone punch all those numbers, press all those numbers into your calculator and see what you get. Is this before you take a square root?
This is before.
Okay, all right. All right, so it'd be the square root of what you say?
1,280,168.
168. Now, I wouldn't throw any of those digits away because this is intermediate. Only your final answer, when you take the square root of that, you get something on the order of 1,000 what? 171 meters squared. What? Oh, 0.8?
It's 31, not 7.
Okay. That's a 31, isn't it? I'd round it to 32. how in the world can you get 6 significant digits when all you have is 2 going in? You can't. In fact, this is a stretch to do that much, but I will allow that. So about 1,132 square meters. Make sense? All right, good deal. Let's see how they did it, which I think is pretty similar. Can I erase? Okay. First, add the 3 up. Divide by 2. That gives you semi-perimeter, which is 84. Then take the square root of Heron's formula, which is square root of 84 times the difference there, difference there, difference there, which would be square root of 84 times 41 times 31 times 12, exactly what we got. And they got about approximately 1,131.89 square meters. Yeah, right. 1,132 is close enough. You've now studied 3 different formulas for area of a triangle. The good old standard thing you learned way back somewhere in your distance past was 1/2 the base times the height. The problem with that, measuring the height. That was always a guesstimate, of what that height was. The oblique triangle, and any one of these 3 will work. 1/2 the base, the 2 sides times the angle in between, the other 2 sides times the angle in between, the other 2 sides times the angle in between. All those 3 will work. The trouble is finding those angles is not easy. Determining the lengths of the sides are not bad, but finding the angle, that's a tough thing to determine. Heron's formula, though, all you need is length of 3 sides. If you got a good tape measure, you can determine the length of the 3 sides and then get the semi-perimeter, add the 3 up, get the perimeter, take half of it. That's the semi-perimeter. There's the formula. Okay. Any questions? All right. That finishes 6.2. Let's do vocabulary. All right. The standard form of the law of cosines for cosine B is equal to a squared plus b squared minus c squared over 2ac is, they just want the other form. What would that be for that representation? B squared is equal to a squared plus c squared minus 2ac times cosine b. You got it. Number 2, when solving an oblique triangle given 3 sides, use the blank form for the law of cosines to solve for an angle. Just depends on what you name it. What they call the alternate form. They call the form they have written up there in number 1 is what they call the alternate form, and what you gave just now was the standard form. So they say use the alternate form of the law of cosines to solve for an angle. But which angle do you solve for?
The obtuse.
The what?
Obtuse.
Well, the largest angle. Whether it's obtuse or not, you solve for the largest angle. The other 2 have to be acute then. So solve for the largest angle, which is the angle opposite the longest side. You're given the 3 sides, go for the angle opposite the longest side. Okay. Number 3. When solving an oblique triangle given 2 sides and their included angle, use the blank form of the law of cosines. What did they call that? Not standard form, but the alternative form. Okay? I think is how they called it. Okay? Form of the law of cosines to solve for the remaining angle. Okay? Number 4. The law of cosines can be used to establish a formula for the area of a triangle called the blank blank formula. Heron's area formula. Very good. Homework exercises here. I would do either any of the odds 5 through 11. They're all at Calc Chat. 9's at Calc View. Then do any of the odds 13 through 23. They're all at Calc Chat. Then do any of the odds 25 to 29. They're all at Calc Chat. 25's at Calc View. Do any of the odds 31 to 35. They're all at Calc Chat. 33's at Calc View. Do any of the odds 37 to 43. They're all at Calc Chat. 37's at Calc View. And then you choose which of the problems you find of greatest interest to you, or you would like to do best, or whatever. any of the odds 45 through 55. Okay? I would say 45 through 59. Okay? I would probably do at least one geometry problem, but the rest of them you do what you choose. Then there's true false, number 61. And by the way, all those should be at Calc Chat. 61 should be at Calc Chat. You can think about doing 63, and 65 is just a writing problem, but you can read about that and see if that's something you might want to do. There's a proof at 67. You can see about that as well. Any questions? All right. Then let's see. What do we have? Oh, we got time. So let's move on to 6.3. And I'm hoping that you'll find this is pretty easy. I think most of you have probably encountered vectors before, yes or no? No? Okay. They're pretty reasonable concepts. I don't think you'll find too hard to follow. And I'm guessing that most of you will be taking physics, right? You will need to know vectors in physics, so this should be motivation enough. Okay? So vectors in the plane, 6.3. Now when they're saying plane, they're not talking about that kind of plane. Okay, that's not what we're talking about here. You can use vectors when flying the plane, but we're talking about a PLANE, which is a flat surface. Okay, that's the plane we're talking about. So, objectives here, we represent vectors as directed line segments. That's going to be the first thing we do. We'll write the component forms of vectors, which is the easiest way to write a vector. So get that down. We'll perform basic vector operations, and you'll find those are pretty easy, and we'll represent them graphically, which may be a little more complicated, but it's still pretty good practice to do. And we'll write vectors as linear combinations of unit vectors, which is a pretty simple thing also. Though it sounds complicated, you'll find it's fine. Then we'll find the direction angles of vectors, which you might think might be hard. It's not. And you'll use vectors to model and solve some real-life problems. I think you'll find those pretty straightforward, too. So let's start with, what is a vector? Well, first, what are some quantities that are always vectors? I'm going to start with something simpler than this. I left home this morning and drove to work. And I'm just going to round off, because I like rounding off, about 20 miles. What I've just described is a distance. Okay. Now, technically speaking, and this would be physically speaking, if I was giving the displacement of home to here, I would also need to give a direction. So I'm going to give a pretty general one and say 20 miles to the southwest. Because I live in Birmingham, and Bessemer is to the southwest of Birmingham, so 20 miles to the southwest. So the first of those was just a distance. We call that a scalar quantity, how far it is, okay? But when I give it a direction, that then makes it a vector quantity, because it's a distance given a direction, okay? Let's go beyond that. If I take the rate at which I was driving, distance over time, that's my speed. It didn't matter which way I was going, that's distance over time, that's my speed. Now, we use these terms everyday life as if they're interchangeable, but they're really not in physics or in math. Velocity is a vector quantity. Speed is a scalar quantity. It just has a magnitude. Velocity is a vector quantity. It has magnitude and direction. Speed scalar, velocity vector. SS and VV, okay? Should be fairly easy to remember. So time rate of change of displacement is velocity then. It has a direction associated with it. Time rate of change of velocity, that's an acceleration. And accelerations, you can talk about the magnitude of an acceleration, but generally accelerations always come with it inherently a direction. And then if you happen to know Newton's second law, which probably most of you don't yet, but you might, that's forces equal mass times acceleration. So velocity is a vector quantity that involves a magnitude and a direction, so is force. Magnitude times a Force, if I push on the desk, I'm pushing on the desk, that's a force, it's in that direction, okay? If I pull on the desk, it's in this direction, okay? A force has a direction associated with it. Cannot be completely characterized by how hard was I pushing. That would be the magnitude of the force, but the force itself had to have the direction with it. So what we use, we represent a vector as a directed line segment, okay? Directed means it has a direction. Line segment means it's finite. Now, a line, by definition, is infinite in both directions. A ray is infinite in one direction, okay? A line segment is finite. It has an initial point and a terminal point. So, by being a line segment, it has a magnitude segment, directed line segment that has a direction. So, we call the first point the initial point, the one from which you're heading. Then the one that you're going toward is the terminal point, because that's where you're going to stop or terminate, okay? And then the vector would be represented PQ, where P is always initial, Q is always one. Listed first is initial, the one listed second is terminal, and the arrow is pointing toward the terminal, always. Don't ever put your arrow this way, that would be really confusing. That's how we represent a vector, okay? A directed line segment has a magnitude, meaning a length, and it has a direction. Okay? It's going that way. Okay? That's not a very precise direction, but it is a direction. The directed line segment PQ, then by definition, has an initial point P, the one that's listed first, and the one that's last is the terminal point, Q. The arrow goes that way. The magnitude, or the length, is denoted by double bars PQ, vector PQ with double bars around it. Now think of it this may not be good. This is how I think of it. Single bars around the number represent what?
The absolute value.
Absolute value, which is always non-negative, okay? Always non-negative. Well, the magnitude of a vector is never negative, ever. That's the length of the vector. You can't have a vector minus 3 feet. I don't even know what that would be, okay? So, it's always positive. So think of this as magnitude is always positive. And it can be found using the distance formula. All of you remember the distance formula? Maybe not, okay? Well, let me get my pen set up. Distance formula is the square root, and I'm going to do it in 2 dimensions now. X2 minus x1 squared plus y2 minus y1 squared. Okay. I don't know if that's how you remember or learned it, but that is a pretty good way to remember it. Okay. That's the distance formula, and that's what we use. Whereas, we'll get into that later. 2 directed line segments that have the same magnitude and the same direction are called equivalent. All 5 of those line segments look like they have the same length, that's magnitude, and they look like they're in the same direction, meaning they're parallel to each other. So those are called equivalent. Later we'll say they're equal, but right now we'll say equivalent. Okay? For example, the directed line segments there are all equivalent, have the same magnitude and same direction. Okay? Now, the set of all the directed line segments that are equivalent to the directed line segment PQ is called the vector in the plane. The vector that has the magnitude of PQ in the direction of PQ, no matter where it's located, that's called vector V. Now, one way they express vectors is initial point, terminal point with a little arrow over it. The other way they do is give it a name, V, but write it in bold. I can't write in bold, okay? So when I'm writing vector V, I put it just like I do PQ, I put the arrow over it. That means it's a vector. The arrow means a vector. The book will use bold. I can't write bold. So vectors are usually denoted by lowercase boldface letters such as U, V, W. By the way, those are the favorites. V being the favorite, just like X is a favorite variable, V is a favorite vector. F is a favorite function name. You can use G or H, but yeah, F is a common. So all these are vectors. You can have other letters too, usually lowercase, but always bold. Okay? Now, there are a few letters that are reserved, and we'll talk about those later. Okay. Here's example 1. It says, show that U and V in this figure are equivalent. In other words, same magnitude, same direction. Which you want to do first, magnitudes or direction? Or do you want to do neither one? Because we run out of time. Okay. So we'll begin next time with example 1. Okay? But since we didn't get example 1 done, there's not much we can do for homework exercises here. Too bad, but you can do them with the law of cosine, so do those from there. Any questions? Yes?
It's about this.
It's what?
It's about this question.
Okay, what about it?
Y value is placed three above, and X value is placed 2 across.
Okay. Yeah, okay. Yeah. Well, you're giving the answer even though we're not going to do it. Yeah. Your change of X is 3 for here, and change of Y is 2. Here your change of X is 3, and your change of Y is 2. You're absolutely right. So that gives the, not quite the magnitude, but it indicates it's got to be the same. And it also indicates the directions are the same. So that one observation gives you the answer to both of them. But we haven't fully worked that out. We'll do it next time. Yeah, good observation. Okay, good deal. We'll see you Thursday then. We'll get through as much of 6-3 as we can.